It's time to move into implementing dynamic routing with RIP. I think this video will come as a sigh of relief after you've seen the static routing video, which works very well if you're paid by the hour in a large organization to set up all kinds of routes around the network so all of our routers and networks can reach each other. But there is a better way, and it's known as dynamic routing. So we're going to take a look at how routing protocols help us, what they do for us. What are the types of routing protocols that are available to us? What choices do we have? And in this series, we're going to focus in on understanding and configuring the RIP routing protocol. To help in understanding how routing protocols help us, I brought back the network diagram, the topology from the previous video when we set up static routes to bring about connectivity everywhere. Now, I've already removed all the static routes from the routers to start in setting up this video, but these routers without any static routes only know about one thing, and that is what they're directly connected to. If I'm looking at router 3 here in the lower right hand corner, you can see that router 3 has an interface connected to 192.168.3 network, so it assumes that it can reach everything starting with 192.168.3. Same thing is true for 192.168.2 over here on the left hand side. So out of the box, once you assign IP addresses to the interfaces, the router realizes that it can reach things on each one of those networks. What does the routing protocol do on top of that? Just tell your friend what you know. Routing protocols in their most basic sense are like gossip. If I turn it on router 3, it will send out messages to all the interfaces that it has running saying, hello, I know about 192.168.2.0 and 3.0. That's all I know about. It's what I'm connected to. Now over here, this router gets it, receives that message, and goes, oh, that's great. I knew about 192.168.2 because I have an interface plugged into that network, so that was of no use to me. But at the same time, I did not know about 192.168.3. That's new information to me. So what I'll do is I'll add that network to my database, my routing table, and I'll make you, the interface that I received that from, the next hop address to help me reach that network. So if we were to look in that routing table, router 2 would say, well, I know how to reach 192.168.3.0, and I'm going to use 192.168.2.2 to get there because 2.2 is the one who told me about it. Now this story continues. If router 2 is running a routing protocol, it's sending out broadcasts and information updates to all the networks that it's attached to saying, hello, I know about 192.168.2.0.3.0 because someone told me about it, and .1.0 because I'm plugged into that network over here. Router 1 gets it and says, oh, well, I knew about 1.0. I'm plugged into it too, but I did not know about 2.0 and 3.0. Great info. I'll add that to my routing table and make you, the person who told me about it, the next hop IP address. So that's how routing protocols help us, is the routers just start spreading information about what they know, and all the other routing protocols in my network will build paths to those networks automatically. It's a little ironic, if you really think about it, that with that concept right there being all that routing protocols do, that's it, that's all they do is they exchange route, that there would be so many choices to make when you're getting into the routing protocol world. You have to think about what protocol you're going to choose and what its advantages and disadvantages are. You might be thinking, well, advantages and disadvantages, if they just say, hello, here's my routes, what advantages are there to that? Well, as we dig deeper, you're going to find that there's a lot of differences between the routing protocols. The first difference is the major class of routing protocol that they belong to. Some routing protocols are considered distance vector routing protocol. I kind of compare those to my very first car that I drove. It was a 1982 Volkswagen Rabbit diesel model. I'll tell you, in the high school days, it was a real babe magnet. It actually, most of the paint was kind of, scratched and whatnot. It was a hand-me-down car. It got 50 miles to the gallon, which was amazing for, a diesel car. But when you're in high school, you don't appreciate that. You want it to go fast. You want it to look great. And the problem is I actually timed it once. It did 0 to 60 in 42 seconds flat. I wrote it down in one of my little journals. I timed my car today 42 seconds. It was horrible, at least for speed, but the beauty of that Volkswagen Diesel Rabbit is that it never died. That car crossed the 200,000 mile boundary. And it was still going strong. And I never changed oil on it. I was horrible at maintenance. That's kind of the class of distance vector routing protocols. They are easy to configure, meaning they're easy to get into. It starts the car up. Well, you got the glow plugs, but outside of that, easy to set up, but not many features. Doesn't really do too much impressive stuff. It just performs the function of everybody will exchange the route. Also, when I say not many features, we have to start thinking about speed, like my Volkswagen Rabbit. If there's a problem in the network, distance vector routing protocols are usually a little slow at detecting that and letting everybody know that there's a problem in the network, so that maybe a backup path would be an alternative. We'll talk more about this, but think of it having a backup connection just sitting there idle for minutes because your routing protocol is just too slow. The two distance vector routing protocols that exist are RIP and IGRP. Not to down RIP, because as I just mentioned, that is going to be the routing protocol that we set up. RIP is all over the place in smaller network environments. It works well for those kinds of environments. It's just when you start moving into the larger networks that have the need for speed, RIP usually comes up short. That moves us to the other side of the coin, the link state routing protocols. These are like the Dodge Viper, really high cost, a lot of training to get into, if you will, really expensive, and just kind of take a lot of maintenance, to keep those things running. But man, are they awesome and fast. They're difficult to configure. They take a lot of knowledge, but they are feature-rific, meaning they are going to support just about every feature a major network will need. The two examples of link state routing protocols are OSPF and ISIS. Those are the two that exist today that are really the Dodge Vipers of our network. Now, the last class of routing protocols is a little hard to find if you look at standards-based documentation. Cisco calls it a hybrid routing protocol, and they're allowed to do that because they made it. They created a protocol called EIGRP. You can see it down here. It stands for the Enhanced Interior Gateway Routing Protocol. What EIGRP does is combine the best of both worlds, meaning Cisco's aim was to bring in the easy to configure aspect of distance vector with the feature-rific aspect of link state to where you can get all the features that you need. That leads to EIGRP. Now, EIGRP is without a doubt one of the best routing protocols that exists, but you can see, as I'm sure you have already, it's Achilles' heel right there. It is Cisco proprietary, meaning you have to have Cisco routers everywhere to run this routing protocol. And some organizations, even if they have all Cisco equipment, routers everywhere, are very hesitant to buy into a proprietary routing protocol because while they may have all Cisco there today, they might be thinking, well, what if someday we want to bring in a different vendor router? Well, we're locked into the Cisco world if we use this routing protocol. So because of that, EIGRP, while it is very popular, you'll see it all over the place, it is not the most popular protocol because of its proprietary nature. Now let's turn our attention into understanding one of those routing protocols, that is RIP. First thing that blows my mind is the algorithm for RIP was first developed in, you're reading that correctly, 1969. Unbelievable, and that is still in production today. We still use RIP in a lot of our networks. Now, RIP comes in two flavors, two versions. RIP version 1, which is the original, and RIP version 2, which adds quite a number of features. Nowadays, Cisco expects that you only know RIP version 2. Or I should say that you only deploy RIP version 2. You'll still need to know that both of these different ones exist and know what the differences are, but today we only use RIP version 2. The reason why is RIP version 1 was a class full routing protocol. Therein lies its weakness. What a class-full routing protocol does is advertise networks but not advertise subnet masks. So let's say that in this network diagram, I actually had the network 172.16.1.0/24 over here. Now that is a subnetted network, looking at that, because by default that's class B, but I put a class C subnet mask on it. So when router 1 advertises that network over here to router 2 receives it as 172.16.1.0. That's all that the advertisement says. It doesn't actually have the subnet mask on top of there. So when router 2 gets it, it's going to look at it and go, well, I've got one of two options. One, I'm going to either assume it's the normal class full version, meaning the normal class B address that's out there, or I'm going to look at all of my interfaces and see if I have one of my interfaces that has a 172.16 address on it. Because here's the idea of classful routing protocols. If maybe I will over here said 172.16.3.0/24 and assign that network on this side, then router 2 is going to look at it and go, oh, well, here's a 172.16 network, and I'm using a /24 mask, so I'll assume this one up here is a /24 mask too because it starts with 172.16. So that's one option. Is it could assume it's /24 because one of its interfaces has it. And the other is if we don't have an interface with an IP address in the 172.16 network, like maybe this was 192.168.3.0 and this was maybe 10 dot something, then it's going to receive that and just go back to the normal class B subnet mask, 172.16.0.0/16. So it's with classful routing protocols in general, it's not that we can't do subnetting. We can. It's just we have to stick to the same subnet mask wherever we go. We can only choose one. And that's what it means by does not support variable length subnet masks. VLSM. That's what that means. VLSM is just changing your subnet mask whenever and wherever you want. Another weakness of RIP version 1 is that it had no authentication. Meaning I could bring a rogue router. I could bring in a router from home. And by the way, finding a router that runs RIP is easy. You can just go pick one up from Best Buy. And I could start poisoning the routing table of my production network just by making up networks and broadcasting them, saying, oh yeah, I've got this and that and the other. And before long, my router starts thinking I've got everything, and all the rest of the network goes down because it's pointing to my little router in my cubicle as the router for the network. So authentication means that you have to have a password of some sort in order to join the RIP routing network. Finally, RIP uses broadcasts, meaning that router 1 and router 2, when they start running RIP, they will start sending broadcasts once every 30 seconds saying, hello world, I know about all of these networks, and advertising them to the whole world, hoping that some other routers will pick it up. Now that's inefficient because you're having all these PCs and all these other devices, printers, servers, everything that's getting these RIP updates, and they're going, oh, I don't know what to do with this, and they just drop it. And top that with these things sending them once every 30 seconds. Every 30 seconds, it's saying the whole life story. Hey, these are all our networks that we know about. That's a lot of network traffic. So RIP version 2 improved that. First off, they made it a classless version. Now, all that means is when these routes are advertised, it advertises what subnet mask is being used for that route as well. Such a simple improvement. And that changed the whole face of networking because now we can do variable length subnet masks. If I want to use, a different subnet mask over here on the right side of the network, I can because my routing protocol supports that. So the way I remember which is better is I always think classless. Just think less is more. Or you might just think, this is the only time it's good to be considered classless. So RIP version 2 is classless, so subnet mask information is sent. They also added authentication in there, so when the routers start communicating information, they also attach a password to that, and that everybody has to use the same password in order to accept the routing updates. So that was a big improvement. And I would say next to the classless thing, the next biggest improvement they had was multicast. Instead of broadcasting to everybody saying, hey, here's all the networks I know about, we used multicast. Now think back to the beginning of this series, and one of the things we talked about was the difference between unicast, broadcast, and multicast. Broadcast is one message to everyone. Multicast is one message to a group. If we set up our network right, the only people who will receive the multicast messages meant for RIP are the routers, the RIP routers specifically. So we won't be bothering the rest of the network with our updates. All right, you have enough of a foundation now in routing protocols to at least know what's going on with them. So let's get into the configuration of RIP, and then we'll do some verification commands, and I'll add some explanation of some concepts as we go through this. So I'm using the same topology as our previous video, but I've removed all of the static routes. So as of right now, router 1 can connect to the ISP, and it can connect to its own local networks, as all these other routers can, but they don't know about networks attached to each other. So if I was on router 2, I couldn't ping behind router 3 because it's not a directly attached network. So what I'd like to do is start setting up RIP, and you can see the three major steps here. One is just turn on RIP, one command. Second is to change the version, and then third is to enter your network statements. The network statements is where most of our concepts are going to focus around. But let's get up to that point, at least in the configuration. I'm going to slide the configuration window into our view here. And I just happen to be plugged into router 2 right now, so we might as well start right there. And let me just get our bearing. Router 2 is sitting connected to 192.168.1 and 2. So I'll bring that up. And first I'm going to do is just do some verification. I'll do a show IP route, and I can see the only thing that I know about are the connected routes. And you might remember the static routes from the previous video, they're gone. So let's turn on RIP. I'm going to go into global configuration mode and type the command router RIP. That one command turns on the routing protocol. It's like you flipped a power switch inside of the switch. It's router and then what routing protocol you want to run. Check this out. Let me get back out. I'll type in router and hit a question mark, and you can see that there's a variety of other choices that we could do. We are choosing to do the RIP routing protocol. So I'll go ahead and put that one's in there. So that's the first step. Turn it on. The second step is now to change over to version 2, because when we start it up, by default, we're always running version 1. So, complex command here. There we go. We're now into version 2. And remember, from the previous slide, that means we're now classless. It means we can support authentication. And it means we're using multicast messages instead of broadcast messages to communicate with our neighbors. Now we come to that last piece, which is enter our network statements. This is the big one to remember. The network command does two things. One is it tells RIP, in this case, what networks to advertise. Probably should have had this written out beforehand, but this is important enough to add in writing. Tells RIPs what networks to advertise. The second thing it does is tells RIPs, so I'll just put little quotes there, tells RIPs what interfaces, and this is going to be some horrible English, but I can't think of a better way to say it, tells RIP what networks to advertise, and it tells RIP what interfaces to send advertisements on. Those are the two things that the network command does. So let me go down to our example here and explain in our example what exactly this means. I'm going to type in a network statement, and the way it works is I type in network and then what network I would like to advertise. So I'll say 192.168.1.0. Enter. Now you can see right here, this router is connected to 192.168.1.0. So first off, this one's the easiest one to understand. It tells RIP to advertise this network. So when RIP starts speaking to its buddies over here in router 3, it's going to say, hey, router 3, I know about 192.168.1.0. And router 3 is going to go, great, I didn't know about that network. So that, I just typed in router 2, advertise that network. Now the second thing is not as easy to understand. Tells RIP what interfaces to send advertisements on. What that means is that when I type in that network command, as of right now, let me just use my undo here. As of right now, router 2 is only advertising this network, and it's only sending out advertisements out this interface. You see that? Tells RIPs what networks to advertise, which I said 192.168.1.0, and I said tells RIP what interfaces to send advertisements on. So since this interface starts with 192.168.1. something, this is the one that's going to send out broadcasts on. Now, it's kind of pointless in this case because the only person who's going to hear that information is router 1. And router 1 is going to say, well, that's great, but I already knew about the 192.168.1 network because I'm plugged into it too. Thanks. So what we need to do is we need to add more network statements. I'm going to type in network 192.168.2.0 and hit enter. Now, RIP is both sending advertisements out, both of these interfaces, because this one starts with 2.0, and it's advertising both of these networks. So now router 1 is hearing about 192.168.1.0 and .2.0, and it's saying, great, I didn't know about 192.168.2.0 because I'm not directly plugged into it. At that point, we're done with router 2. That's the complete configuration of the RIP routing protocol on router 2. There's no more to it, and that's the easy to configure aspect. Now I just need to go to these other routers because as of right now, router 2 is sending the updates, but since RIP isn't turned on router 3 or router 1, they're getting them and just dropping those updates. So let me jump over here. I'm going to exit back out of router 2, and I'm going to hop over to router 3. So now I'm sitting on router 3. From here, I'm going to do the same configuration I did on router 2. I'm going to type in router RIP and version 2 to convert it over. And now I need to tell it what networks to operate on. So I'm going to look back at my diagram. Router 3 is connected to 192.168.2.0 and 3.0 over here to the right. But I'm going to do this in phases. Watch this. I'm going to type in network 192.168.2.0. 2.0. Let's just do that one first and see the results. Now what that does is tell router 3 to begin advertising this network 192.168.2.0 out that interface. Now, router 2 is going to get that and be like, great, buddy, I knew about the 2 network. I'm plugged into it. But more importantly, router 3 is now going to be receiving and understanding the updates from router 2. So it should, if everything's working correctly, learn about 192.168.1.0 up here. Now, this is all going to happen automatically now that it's turned on. So let's do a show IP route. I hit enter. Check it out. We've got 192.168.1.0, which is now sitting in our routing table. First off, look to the left, and you see that we have RIP as our code as how it learned about this network. Now, right next to that, you see the subnet mask for the network, but we see 120/1. 120 is considered the administrative distance. It's how believable the routing protocol is. Essentially, the lower the number, the more believable the routing protocol. Here's the idea behind that. Let's say that I had, of course, this topology wouldn't lend itself to this, but somehow I had a connection over here to router 1. And instead of RIP, we were using OSPF between these two routers. Remember the Dodge Viper? It's the fast routing protocol, link state routing protocol. We were using OSPF as the communication between router 1 and router 3. Well, in this case, router 3 is going to hear about the 192.168.1 network over here from both router 1 via OSPF and from router 2 via RIP. So now it has to come to the crucial decision, which one do I believe? Well, OSPF is the better routing protocol, and because of that, it actually has a lower administrative distance. OSPF actually shows a number of 110 right there. So if I were really running OSPF up here, router 3 would believe that because it is more believable. It's a better routing protocol, and thus I would see an O route in the table, which would represent our OSPF right there. And this would say 110 because it would be a more believable route. So that's what that first number is how believable is that route? The second number is technically the metric, or how far away is that network according to this routing protocol. So in this case, RIP is saying that the network 192.168.1.0 is one hop away. That is because RIP uses hop count as its metric, where a hop is a router. So router 3 sees 192.168.1.0 and it goes one hop, bounce off router 2, and I'm there. Whenever I think of hops, I think of, remember the old arcade game Q*bert, where you were kind of jumping around on a pyramid of squares? That's what I think of, is you're just kind of hopping, where those hops are routers. So router 3 is going through one hop to actually get there. Router 3 itself doesn't count as a hop because that's the point you're leaving from. So wow, I've got a lot of scribbles on here. Let me just clear this out so we can get some more, oh, that worked well, some more drawing going on. There we go. There, that's all I need. Just some area right here where I can get a little clean slate. So we've got, see, I can't do two things at once. There we go. We've got router 3 now knowing about 192.168.1.0 because via router 2 advertised it via 192.168.2.1. This address is the next hop address, meaning router 3 goes to router 2, right there, 192.168.2.1 to reach 192.168.1.0 network. So you can see, you can almost read this thing backwards. Hey, let me start from the far right side. I'm going to go out serial 0/0. Well, router, why are you going out there? Well, because if I go out that interface, I get to 192.168.2.1. Well, why are you wanting to reach that? Well, because that router can get me to 192.168.1.0. See how you can kind of have a conversation with a router on these things, where this is the exit interface, and you kind of read it backwards and put this solution together. This is the network that I'm now able to reach. Now, before we do any more configuration, I want to hop over to router 2 and do a show IP route. Now you can see router 2 does not yet know about anything. It still knows about its connected interfaces, and that's it, because we have yet to put the network statement on router 3 that tells it to advertise 192.168.3.0. So let's do that. Oops. Get my windows in order here. I'm going to hop over to router 3. Go back into router RIP. I don't need to type all the version 2 and all that because it's already there. I'll just type in network 192.168.3.0. Enter. I typed that in because this is the network that I would like to advertise. And as a side note to that, RIP is now sending advertisements out that interface. So if there are any other routers over here, they could actually receive those updates. So I'm going to jump back over here and look at router 2. And now I'll do the show IP route again. Now notice, right up here, we saw before there was no RIP routes. Now I do a show IP route. Look at that. We now have a RIP route that has appeared to the 192.168.3.0 network. I'm getting there via 192.168.2.2. That's router 3. It's the next hop address. And I exit my serial 0/1/0 interface. That's the interface on router 2 that it leaves to get to that network. So almost all the pieces of this puzzle are in place. I'm going to now jump up here to router 1. I don't have an open session to that, so let's telnet to 192.168. Let me look at its IP address. It is 192.168.1.1. All right, got our logon banner. I'm going to type in my username and password. So I'm now on the CBT router sitting up there. I'll do a show IP route, and oh, bummer. I forgot to remove the static routes. Well, you know, as a bonus, I planned this because I'm going to do a show run, and I want to show you some cool tricks that you can do with the show run command. See how I turn my forgetfulness into a learning experience? I can type in show run, but when I hit the question mark, notice it gives me some options. The one I'm interested in right now is this pipe. Now that little line right there, it's known as a pipe. It's the one above your enter key on your keyboard. If you do the shift \, you put that little pipe symbol. And what that lets you do is filter the running configuration output. A lot of people call this regular expressions, but it's actually simpler than that. I'm going to type in show run, and a pipe, and I'm going to say include stuff from the running config that has IP route in it, because I know all of my static routes start with the command IP route. You see that? Now I can pull all my static routes from the running config without having to scroll through the whole thing. See, what a shortcut. Now let me show you yet another shortcut. How to remove static routes. No. Anything with no in it negates the command. So I'll do no and just paste that in from the running config so I don't have to retype it all manually and hit enter. One of them are gone. No. Right click, paste that in there. Two of them are gone. So now when I go back and do a show IP route, I can see that the only thing left is my default route, and I'm going to keep that one in there because that's what's going to grant us internet access. You'll see that a lot of times the best solution to your Cisco network is a combination of dynamic and static routing. It's typically static routing used for your default routes. Side note one more time, before we enable RIP, I want you to see that first number is the administrative distance of a static route. 1. Do you remember RIP? If we scroll back up here, up, right there, RIP was 120. The lower the number is, the more believable it is. So static routes always beat RIP routes because the router assumes you know what you're doing. 1 is one of the best administrative distances or believabilities that you could have. So let's get CBT router enabled for RIP, and I want to point out a key point as I do this. First off, I'll type in router RIP version 2. So it's now running version 2. Whoa, almost lost my mouse there. Let's come back to the network diagram. I want to turn it on first for 192.168.1.0. So let's do that. Network 192.168.1.0. Enter. We're now running RIP on the 192.168.1 network. Now, with the updates being sent once every 30 seconds, we may or may not have received an update from our neighbor. I'll do a show IP route. Oh, looks like we did. Good news. So we can see that we have a RIP route, 2 RIP routes that have been learned, 192.168.2 and .3.0, which represent this WAN link and this network back here on the right-hand side. Router 1 now knows how to get there. I can see that one of them is admin distance of 120 and 1 hop away. The other is admin distance of 120 and is 2 hops away. You see that? This is the 3 network, so that makes sense when we look here and go 1 hop, 2 hops, and then I'm there. That's how the hop count works. I can see the next hop IP address that I'm going out and how I can reach that. Now that is a complete end-to-end RIP scenario. I can ping, 192.168.3.1, and I'm getting there. Life is good. We're chugging along and reaching those networks. But the thing that I wanted to show you on this router was, let's say I wanted to advertise my ISP link to the rest of the routers via RIP. Meaning I want router 2 and I want router 3 to know about this network between me and the service provider. How would I do that? Well, I get right back under RIP and I go into network. Oops, wait a sec. Router RIP. I'm under the RIP process and I need to type in a network command, but this is where the catch is. A lot of you might look at this, as would I, and say, well, we need to type in network 68.110.171. And find out the network for that subnet mask. But that's actually not how RIP works. RIP, being a very old protocol, wants you to type in the networks as if they were class full, meaning as if they were their default class. Now, looking at that first number on this internet address, what class is that? Well, class A is 1 through 126 in the numeric scale. So that is a class A address. And class A addresses have the default subnet mask 255.0.0.0. So when I type in my network statement, I need to type it in network 68.0.0.0, as if it was a class A address back in the 1970s before we did any subnetting on it at all. What that tells RIP is advertise any interface that starts with the number 68 into the process. Enter. Now, when I jump back over here to router 2, I'm going to type in show IP route. Let's see if it's learned about it. Oh, wait a sec. Nope. I didn't jump back. I'm still on the wrong router. I'm back on router 2 now. I'll do a show IP route and hit enter. There we go. Look at this. It shows a RIP route, a class A address. You see that subnet mask, a /8. A class A address is 68.0.0.0. Has now, it's been summarized, if you will, back to the way it was when the internet protocol was first designed, before any subnet masking took place at all. So that is one of the disadvantages of RIP, is that by default, it looks at these as, class full, without subnetting. Now, it's not really part of this curriculum, but I want to show you a command. Whoops. I'm going to go back on that CBT router. By the way, this is the one with the internet route, just to get us our bearings again. This is the internet router sitting up here, router 1. And I'm going to go into router RIP and type in no auto summary. I'm going to run around to all of my routers. If I could get my bearings here. I'm going to type in on router 2, router RIP, no auto summary. Control Z. Jump back out, go over to router 3, router RIP, no auto summary. Enter. What that does is keep RIP from automatically summarizing this back to what's known as the classful network, back to its class A address. So I'm going to go back to router 2 now and do a show IP route. And now you can see, look at this. I see a RIP route that it's learned about, the 68.110.171.96 network. If we were to reverse engineer this subnet mask right here, I would find out that that is the network ID, the very first address. Remember the one that's not usable? The very first address of that subnet would be 96. The increment on /27 is a 32 increment. So that would be how I could reverse engineer that subnet mask, and I would see this is the network that I now know about. Now, this one will eventually disappear. It'll reach its timeout value from my routing table. So that is the RIP routing protocol. The key point that I want to make sure that I point out to you, I'll do a show run. When you're configuring RIP, you want to make sure that the network statements that you type in, here we go, the network statements that you type in are the class full version, meaning you have to type in those addresses as if they were the class A or class B default, even if you have that no auto summary command in there. Now, in the real world, if we make a mistake, if we were to go under router RIP and type in, network 68.110.171.96, which is the real network, in the real world, the router takes it, and when we go back and do a show run, we'll find out that the router fixes it for us. It goes, oh, well, you really meant the 68 network. It kind of undoes what we just did and summarizes it back to the class A. On the exam, if you're interested in certification, the simulators will take it as well, just like the router does, but it won't fix it for you. It'll deduct points. So you want to make sure that you keep that in mind. So I know that looked like more work than static routing, but that was just because I was kind of teaching as I was going. Really, all you had to do was get in each one of those routers, type in those network statements, and now all the routers, let's just do one more glance at router 3 over there. All of the routers know about all of the networks in our organization, and they are now able to reach those networks because RIP is doing the work for us. It's a lot more efficient than static routing. That is the process of implementing dynamic routing with RIP. So let's hit the high points. Number 1, we saw how routing protocols help us, and they do that by essentially telling each other what they know, the connected interfaces, and it just grows from there to build a routing table. We then looked at the 3 types of routing protocols: distance vector, which includes IGRP and RIP, link state, which is OSPF and ISIS, and finally, hybrid networks, which are EIGRP. Hybrid combines the best of distance vector, which is the easy to configure side, and the best of link state, which is the featureific side, into one protocol known as EIGRP. Last thing we did was understand and walk through the configuration of RIP. Oh! Darn it! I just remembered. There's one more command I wanted to show you. Let me just bring this back into focus. It's on the summary slide. It just crossed my mind. It is the show IP protocols command. What this does is show you whatever routing protocols are running on your router. If you're on a router at work and you're wondering what routing protocols are running, type in show IP protocols. You'll see RIP sending updates every 30 seconds. Next update is due in 2 seconds. You can see what version it's sending right here. You can see what interfaces it's working on right here. You can see the networks that it's routing right here and what neighbors it's heard from down here. So a lot of good information about RIP can be displayed from this. We can also do a debug IP RIP. Man, see, now all these things hit me. Of course, as I'm summing up. We can do a debug IP RIP, and we'll be able to see in real time as we are sending updates, and we can see on router 3 is sending updates out about these networks, and down here it received an update from one of its neighbor about these two networks. The update came in, and then it sent another update. You know, once every 30 seconds, it's going out all the interfaces, sending updates. You know, coming out here. So I mean, you can see a lot of information from that debug in real time. Be careful with debugs in production because they can bog you down. You can turn that off by typing in no debug IP RIP, or the shortcut to turn off all debugs is use space all. And that will turn off all the debugs. So there we go. Now I can get back. That is understanding and configuring and verifying that RIP is running. I hope this has been informative for you, and I'd like to thank you for viewing.